Hello everyone. We're going to be doing questions on Stokes laws and okay. So in this experiment, uh, we're trying to find the viscosity of glycerol when dropping a metal sphere, down a cylinder of glycerol. It has radius 4 millimeters, and it reaches terminal velocity and takes 3.9 seconds to fall half a meter. So we're trying to find the viscosity of glycerol, and we're going to be using mainly two equations. So first is the equation for viscous drag force, which is Fd equals 6 pi times eta times r times v. V is the velocity of the steel sphere, and we are also using the equation for the buoyancy force, which is rho, the density of the fluid, times the volume of the fluid displaced, times gravitational acceleration. Okay. So the first thing we need to do is to draw a free body diagram of the sphere falling down the tube of glycerol. If the sphere is falling at a constant speed, which is because it's in terminal velocity, it's traveling at a constant speed, we know that the forces on the sphere have to be in equilibrium. And so as the sphere is traveling down because of is being a force acting on it downwards due to its weight, m times g, and this is getting counteracted by both the buoyancy force, which is rho times v times g, and also the viscous drag force, which is 6 pi eta times r times v. And we're trying to find eta right here, which is the viscosity of the glycerol. So we have all these numbers, and I think the best thing we could do right now is let's start by converting these numbers into the units that we're going to use. So first of all, we need to convert 4 millimeters into meters. That is, I think 4 millimeters is 0.004 meters. That's the radius of the sphere, and it travels. Yeah, I think that's it. Okay. So we also need the velocity that of the fluid displaced is actually just the velocity of the ball when it's traveling down. So we can use the equation 4 pi over 3 times r cubed for the velocity of the ball. For the volume of the ball. My bad. All right. So if we set out the equation, and we don't want to substitute the numbers in right now because it'll be an absolute mess, especially with how small 0.004 meters is, and when you cube it's going to get even smaller. It's a whole heck of a mess. So I think what we want to do is just put the equations together and then rearrange it to isolate eta, the viscosity of the glycerol. So let's say that all the forces going up are positive and the forces going down are negative. This means that the buoyancy force and the viscous drag force plus and then minus the weight is equal to 0, as there's a 0 net force, right? Okay. Oh, I should say this is the summation of all the forces. My bad. Okay. So we want to rearrange this to isolate for eta. And this is just, we're going to do a little bit of algebra. So this will be mg. You can probably skip through this, actually, if you don't want to watch me do this. All right. So that is the equation we rearranged for eta, and we're going to rewrite the So actually, I just realized they gave us the density of the steel, but they didn't give us the mass of the ball. So we're going to rearrange the mass. We're going to substitute the 4 pi over 3 4 pi over 3 times r cubed. My bad, I wrote this here. 4 pi over 3 times r cubed into this and this to be able to substitute things in. So mass is the density of the ball times the volume of the ball, which is 4 pi over 3 times r cubed. So this is the mass, and this is, we also need to times it by the gravity, which is 9.8. Then we have to take away the density of the fluid and times it by the volume of the fluid displaced, which is just the volume of the ball again, and times that by 9.8. This is all over what we had before, which is 6 pi times r. 6 pi times radius times velocity. And so now when we substitute the numbers in, the density of the ball is 7,800 kilograms per meters cubed. 7,800 kilograms, I believe. Yep. Times, again, you can probably skip through this, or if you're running at 2 times speed, this should be quite fast. The radius is 0.004. The main idea is that you understand how to do this question. That's the biggest point here. Once you get it down, you can probably do all the other questions of the same type. Density of glycerol is 1,300 kilograms per meters cubed. This is all over 6 times pi times 0.004 times and the velocity of the ball. Oh, we haven't found the velocity of the ball. Okay, we can just equate it as 0.5 meters in 3.9 seconds. There we go. Alright, so I'm just gonna plug in the numbers, and you can probably skip through this. I'm wasting a lot of your time. My bad. Okay. This gives us a viscosity of 1.766. I completely forgot the units for this. I think it is Pascal seconds. I'm actually not quite sure. Well, whatever it is, I know it. Okay, so the unit for this is kilograms per meters per second. All right, my bad, guys. Should have prepared better. So this is the answer here, and we're going to round it to 2 significant figures. All right. Okay, so let's move on to the next question. And this is the right answer, by the way. So there are 2 cylinders available for the student to use. One cylinder has a diameter of 1.5 centimeters, and the other has a diameter of 5 centimeters. So we want to state and justify which cylinder we want to use to have a better and a more accurate measure of the viscosity of the glycerol. So a quirk of all these Stokes laws questions is that they really care about laminar and turbulent flow. So if you imagine if you had a small cylinder like this, in relative to a big cylinder like this, you're going to have the ball here, right? The ball is the same size. But if you imagine, in the small cylinder, there's going to be like kind of turbulent flow, right? As it displaces the fluid as it goes down, there's not much space for the fluid to move. Well, in here, the fluid has a better chance to move out of the way of the ball, and so actually doesn't like stop or drag the ball down that much. And so what we want to state is that we want to use the 5 centimeter diameter cylinder. And we also want to state why, and that's because the small cylinder has more turbulent flow. And so Stoke's law will not apply, because Stoke's law only applies if something is moving at its terminal velocity when all the forces are in equilibrium. If there's turbulent flow, sometimes it's going to be accelerating upwards. You know, so it's inaccurate. So we want to state that with turbulent flow, Stoke's law won't apply. And so that means that it will be inaccurate. All right. That's we stated our choice here, and we justified our choice here. And remember, Stoke's law questions love to talk about laminar and turbulent flow, so make sure you keep a heads up for this. And here's the mark scheme for the questions if you've been doing it as I have been. So you can check here, take a screenshot, whatever, and I'll link to the questions, like a whole sheet of questions, even questions I haven't featured on here, a whole sheet of questions about Stoke's law later. So we're moving on to the second set of questions, and let's analyze this. Okay, so a photograph shows a type of drink known as stout. When the drink is poured, it contains many spherical bubbles of gas, which rise and form the foamy head at the top of the drink. The manufacturer of the drink states, it takes 120 seconds for the head to form. For the smallest bubbles, the uniform upward velocity can be calculated using the equation. And here's the equation. Derive this equation by considering the forces acting on the bubble. So again, it asks us to consider the forces acting on the bubble. So we want to start off by drawing a free body diagram again. But this time, the bubbles are going up. So the directions in which the forces act on so it's still going to have a buoyancy force going up. It's still going to have weight going down, which we'll denote as mg. But there'll also be the viscous drag force. The viscous drag force that's also pulling it down as it opposes the direction of movement of the bubble, right? So, and I'll state the equations again here. So 6 pi eta times r times v, and this is rho times the velocity times gravitational acceleration. Okay. Oh, I dropped my pen. Okay. Oh no, did I break the tip? I think it still works. Okay. So this time we want velocity on the other side. And we want to consider the difference. So if you see here, we see that there is a difference between the density of the stout and density of the gas. So we can tell straight away that we do not want to be using mass, but rather we want to be using the density of the gas times the volume of the gas, which is 4 pi over 3 times r cubed, then times gravity. And then I think yeah, because we don't know what the volume of the thing is. We also need to, this is the density of the stout times 4 pi over 3 times r cubed, and then times gravity. Okay. We want to set up an equation that represents this. And instead of doing the sum of forces like I did on the first question, I'm going to show you a different way of setting these equations up. Both is fine, but you can choose which one you'd like to do. So here, we know that the buoyancy force has to be equal to the sum of the weight plus the viscous drag force. So we can set up an equation like this. The density of the fluid times the volume of the fluid displaced times the radius, this is the volume, times the gravitational acceleration is equal to the viscous drag force plus the weight, which is the density of the gas times the volume of the bubble times gravity. Okay. So now we want to isolate velocity, and we're going to leave the velocity on the right because it's already on the right. So what do? We keep the buoyancy force on the left, and then we minus the weight of the bubble. And like before, you can probably skip through this as long as you understand what I'm doing. And over 6 pi. Okay. So if you look on the top here, we can see that it's factorizable because we have the density of the stout minus the density of the gas, and that's all times by the volume of the bubble times gravity. So in other words, we can write it like this. And we can cancel some things out as well. So pi cancels out, r cancels down to r squared, and we can also take 4 over 3 divided by 6, which gives us 2 over 9. And you can check this with your own calculator by yourself. But we'll end up with 2 times r squared times g times by the density of the stout minus the density of the gas over 9 eta. And voila, that gives us the equation that we're looking for. Okay, so as long as you understand the process that I reach here, and most importantly is understanding the forces occurring onto the bubble, and being able to substitute the mass with the density of the gas and the volume of it, and all these things, and then setting it into an equation like this, you'll be fine, right? So let's move on to the next question. State an assumption you have made. Again, these Stokes law questions seem to be really focused on turbulent flow and laminar flow. So an assumption that we made is that this ball is this gas is traveling at terminal velocity, right? We're assuming that there's no like turbulent flow behind it, dragging it down and decelerating it. And so an assumption that we've made is that there is no turbulent flow. Okay. And you can also say there is laminar flow and it's moving at terminal velocity. In general, just write that there. So laminar flow and terminal velocity. Okay, let's move on to the final question. Okay guys, I'm sorry for having another cut. I keep making like small mistakes and it's really annoying, but okay, so starting with the third question, so the manufacturer states that it takes 120 seconds for the head to form, which is the gassy thing on the top when you pour your Coke, right? So you want to consider the time for the bubble to travel from the bottom of the glass to the top. And we already found the equation for the velocity. And velocity is just distance over time. So we can rearrange it again to isolate the time. So first of all, we need to convert these units into the units that we'll be using, which means meters for this, which is 0.115 meters. And diameter of this, so first of all, divide this by 2, which is 61 micrometers. And also, this is 61 times 10 to the power of minus 6 meters. Okay. So now that we have the equation, we have the units ready, we simply substitute. But what we're going to really do really quick is that if velocity equals distance over time, and if velocity is equal to something, so distance over time, and velocity is equal to, let's say, x, to isolate time, we need to take the distance and divide the distance by x. So in actual fact, let me rewrite this. So in actual fact, if distance over time equals x, then time equals d over x. And so how we're going to rearrange the equation is that we're going to have time is equal to distance over 2 times r squared times g times the density of the stout minus the density of the gas over the 9 times eta. 9 times eta. Okay. Alright. That should be what we need. Yep. So we simply substitute the numbers in. And so this would be 0.115 meters. There's a lot of we're going to have to use a lot of standard form here. 2 times r squared is, the r is a tiny number. 61 times 10 to the power of minus 6. And this is all squared times 9.8 for gravity. And then times the density of the stout, which is 1.01 times 10 to the power of minus 3, 10 to the power of 3, minus 1.22. And this is laid out horribly. That is all over 9 times the density of the viscosity of the stout, which is 2.06 times 10 to the power of minus 3. And so I'm just gonna plug this in the equation real quick. Plug this into my calculator. You can probably skip this, guys. Okay. So we're left with the time of 28.979 seconds, which rounds up to 28 point. Actually, just rounds to 29 seconds because the smallest accuracy is 2 significant figures. And so, now that we've found the time, we need to evaluate whether the statement from the manufacturers is correct. Would the head really form in, would it take 120 seconds for the head to form? Well, the mark scheme does reward different ways of thinking here, but I think the best way for you to answer this question is to look at the previous question right here. State an assumption you've made, and we've assumed that there is no turbulent flow, that there is laminar flow, and that the bubble is traveling up at terminal velocity at constant speed, at the speed that is as fast as it can. But that could not be true. There can be turbulent flow, right? Turbulent flow slowing the bubbles down. So here, Stokes' law, while it does find the minimum time that it takes for the bubble to reach up the top, might not be accurate. And so this leads to the head forming later than the minimum time. Okay, so that's it. That should be the answer over here, and you can see the mark scheme right here. You can take a photo again, and I'll link to the sheet of questions that I've used. This question really like drained the sanity out of me, guys. Stoke law sucks. It really sucks, and thank God I made a video for this. Anyways, thank you guys for watching. Now I have to edit like 4 different videos together. All right, thank you.